this lecture is under the Erasmus Plus program and we are teaching VLSI, this also affects what we teach. And one of the conclusions of my lecture that we need to teach also not only VLSI, if you want to teach VLSI design, we need also to teach technology and semiconductor physics. It's not enough just to teach. By the way, if you think about it, 7 nanometer CMOS and the size of DNA is about 2.5 nanometer in diameter. And by the way, it can be much, much longer. So our transistors are not much bigger than DNA molecule. So what are the challenges? So we all know that, for example, if we look at the memory chips, early memory chips were very large and we use different CMOS, different devices. And then of course, recently, everybody switched to SoC, system on a chip. And we have a high CMOS, low power CMOS, dense memory, analog, I/O, everything integrated. And what we will have in the near future? In the near future, we have two things. One is the 2.5D integration and the 3D. And this is what I'm going to talk about later. And this is the current CMOS nodes are the 60 nanometer, 10, 7, and the advanced 7, which is available today in the foundry. And I will not go to further details. 5 nanometer is actually also available, but I'll switch to this. I'll switch this. How this become? If you look at how this becomes available, this is the node density, 1 million transistor per millimeter square. But I would like you not so much to focus. Sorry, I moved to a different slide. I would like you please look at this. This is technology. You have here, we have the transistors inside, but look how beautiful are the lines, are defined, how sharp are the corners, and this is talking less than 5 nanometer technology. So how do you do 5 nanometer technology when you use optical lithography? The trick is to use enhanced or extreme UV technology. So, CMOS scaling, there are 4 thrusts today, which affect the future. One is the heterogeneous system integration, the 2D integration of system on a chip, and the 3D integration of silicon on a package or system in a package. We have the 3D process and design, which is coming soon. Then you have novel functions, like novel devices. And then we also have novel data processing architecture. Not just a phenomenal machine. I'm going to show later some new innovations, but maybe different type of machines. For example, new devices and materials, if you're all familiar with resistors, you're all familiar with capacitors, you're all familiar with inductors. I think most of you are less familiar with memristors. Memristor is kind of the missing link in all this, because we have voltage and current and the integral of the voltage and integral of the current. So since we have 4 variables, we need to have 4 devices. Nobody is using memristors, so very few people are using memristors. Everybody is using resistor, capacitor, and inductors. Maybe using memristors, we can get a much better circuit for some specific applications. The only problem was that memristors were not available commercially. However, due to recent invention, using titanium oxide memristors, when you you have this very thin oxide. It's very thin oxide. And if you have this very thin oxide, you have positive charge make the device more conductive and negative charge make it less conductive. And you can make this resistive device with memory or memristor. And you can integrate it and make some interesting devices. And one of the, and this is I mean, the memristor itself was conceived by Professor Leo Yao 30 years ago, but only now you can see some devices, and Memristor-based network, when you make this interconnect and the memristors in between, and the memristor is formed at each cross point. This is a cross point design and can be used to simultaneously store data and process information. So this approach, vector matrix multiplication, can be obtained through Ohm's law and Kirchhoff's law through a simple read operation. In addition, the internal dynamics of memristors can be utilized to faithfully emulate underlying processes in biological synapses. So we can make some very fancy and interesting devices using memristors. So one approach in future devices, in future VLSI, is to use some novel device, and the most pronounced is the memristors. You can also look at flash memory, DRAM, new memory concepts. And this I took from recent presentation in also in ISSCC. You can look at, if you look at computers, in every computer you have storage and memory. You have storage, computing, and memory. So you have the CPU, level 1, level 2, level 3 memory, main memory, and all other memory devices. Why not having DNA storage? Why not having magnetic random access memory devices? Or something which is more true is the 3D dynamic random access memory, 3D FEFET, and 3D NAND, stacking more layers. Actually, this is already almost available today. So let me show some future devices. For example, flash memory scaling. The concept is first stacking more layers. You build the device vertically, and every point here is a cell, and this is like a NAND cell, but a vertical NAND cell. Also, you do multi-level devices, so the number of cells you can, and this is V threshold of the devices, you can make a multi-level cell. And then maybe instead of using silicon, use high mobility materials. This was taken from a lecture of 2017. So one way of flash scaling is making multi-level scale, making it three-dimensional. The memory element, instead of making the transistors that I showed you before, if you remember, one of the things, if you want to store more charge, you increase the capacitance. One way to increase the capacitance is making it vertical. It looks like a cauliflower, or making like a very large area. So this is how it looks. This is, you make your, this is a FinFET for DRAM periphery. So you can make it, you use FinFET for your DRAM. And you use a memory element, which is much longer, which is much higher capacitance. You can make it smaller in the lateral dimension and bigger in the vertical dimension. This is, again, you make a better design by making a better technology. And this picture is better because the previous one, if you're not an expert in technology, is difficult to see, but this picture is explaining the previous one. In the regular device, as I showed you before, you have the source and you have the drain, and this is the conduction, and you store the information on the floating gate. In a vertical device, this is the silicon conductor, and this is the storage gate. And that's why, if this is a single cell, we mark it this way, we can stack them. We can put one on top of another and make a vertical integration, etc. So by making a vertical device, we can stack them vertically. This was presented in 2020, very recent. And this is a NAND or a NAND flash. So in a NAND flash, sorry, you can make a vertical memory device. And because of that, you can store more bits per unit area. So what else? The other things, instead of in a regular device, instead of having one threshold device, you can have a multiple V threshold devices. And if you look at V threshold distribution width, if you make a technology known, this is the 50 nanometer, 40, 30, 20, 10 nanometer. And here the V threshold distribution was actually pretty large. If you make the 3D NAND, in the 3D NAND, because you're not so stressed in the lateral dimension, you can make the device with a little longer length of the gate, and you can get much better VT distribution. So you can get much better reliability. So moving from a 2D NAND, which is a lateral NAND, to a 3D NAND, which is a vertical, and it's a gate all around. The gate, as you just showed you before, let me switch it. Okay, see, this is the lateral 2D, this is the vertical. In the vertical D, the channel area is larger, but the number of electrons per area is much larger, and the interference is much less. So we can match about, on one hand, it's a much better flash. Also, it's many more bits per unit area because everything is stacked vertically. As I showed you before, this is called the COA, CMOS under array. One way to improve the device is, one way to do it is, why making everything, sorry, switching. This is like a cross section. This is my CMOS device, and this is my gate and the bit line. So if these are the word lines, so these are the vertical device, we put all the CMOS circuits under, we put the NAND flash on top and the bit line on top of everything. So this is the CMOS, this is the NAND vertical flash, and the bit line on top. And since everything is vertically, and this architecture is called COA, CMOS under array, it's a floating gate cell 3D NAND with a CMOS under array architecture, polysilicon, and this system using the GIDL, the gate-induced drain leakage lowering, to erase the system. I will not go to the physics, but you can see that if you want to design this type of cells, you need to understand short channel device physics. So this is not trivial. And this is, by the way, this is how it looks from the cross section. And this was actually presented first time in 2015, but it's still only now in full manufacturing. So it's already, this lecture about the future of VLSI, but the future is now. The advantage of, okay, I already talked about it. I can make, the 3 NAND, the number of electrons per 1 volt delta VT is less, so it's, we can get better performance. Or maybe use a completely different device. Maybe use magnetic memory for cache replacement. Instead of using CMOS, we can use spin transistor or spin orbit torque or magnetic anisotropy. And there are a lot of these devices are being developed by a few companies and few places. Still not in full manufacturing, but this technology is ready for manufacturing, not in high volume manufacturing yet. The spin orbit torque device is in research, and the magnetic anisotropy device is exploratory. So this is real future. So what about new circuits and technology? And again, I took this, there's a lot of people in the waiting room, so please allow them to enter. So if we talk, now let's go to the final stage of this lecture. We have 10 or 15 more minutes before I allow some questions. Let's talk about real devices. As I told you, the beauty of this lecture that I have to update it every year, because if you look at the 40 nanometer AMD EPIC Gen 1 processor, which was 8 to 32 cores, 180 watts and 2 terabytes of memory, by the 7 nanometer, the Gen 2 is 8 to 64 cores, 225 watts and 4 terabytes. You can see, by the way, by making it smaller, we aggravate the power situation. 225 watts is not an easy task to to dissipate. But if you think about it, if we reduce power by 20 and the cost by 10, 25 racks